Students, in this video, I am going to discuss singular integral equation, solution of singular integral equations. So first, what is the singular integral equation? Singular integral equation. An integral equation in which the range of integration is infinite or in which the kernel is discontinuous is known as singular integral equation. So either the range, for example here, range is infinite, or in which the kernel is discontinuous. For example here, if you put t is equal to x, this limit, t is a variable, x is the upper limit. If you put t is equal to x here, this will be infinite. So that's why not defined, that means discontinuous, and hence in which the kernel is discontinuous is known as singular integral equation. Examples are these three. So here in the first example, if you will see, limit is infinite. This is limit is infinite. That's why both these examples are saying that the range of integration is infinite. That's why they are singular integral equation. However, the third example here, when t is the variable and x is the upper limit, when you put it here, t is equal to x, this will be infinite, and hence this is the kernel is discontinuous. That's why this is second category. So these three are the singular integral equations of first kind. Now we have a very special kind of singular integral equation known as Abel integral equation. So the solution of Abel integral equation. What is the Abel integral equation? So this equation is given by this. F of x is equals to integral 0 to x yt divided by x minus t raised to the power alpha dt, where alpha varies from 0 to 1. This is known as Abel integral equation. Fine. Here this function is basically known function, while yt is to be determined. This yt is our unknown function, f of x is the known function. Fine. So our interest is to find out y from this equation. So to solve, so suppose we will designate this equation as equation number 1. Now to solve this equation, multiply 1 by 1 upon u minus x raised to the power 1 minus alpha, and then integrating with respect to x from 0 to u. So this is the limit. So take the integral here, integral with limit 0 to u, and multiply this f by this. So f of x divided by u minus x raised to the power 1 minus alpha, and then dx. So we first multiply by this here, and then integrate. So this is the left hand side equal to. So now integral 0 to u, multiply this integral by this factor. So 1 by u minus x raised to the power 1 minus n, and this factor is 0 to x yt upon x minus t raised to the power alpha dt, and then dx. This is equation number 2. So now to solve this the right hand part, apply change of order. So to change of order, first construct the strips or the area. So here first we are integrating with respect to t and then with respect to x. So what is the limit of t? 0 to x. So this is t axis, this is x axis. Now here t is 0. T 0 means this axis. Then t is equal to x, that means this 45-degree angle, because this is x, this is t. So t is equal to x means this line. So we are moving from here to here. Now second is limit is for x, where x varies from 0 to u. X is equal to 0 means this axis, and x is equal to u is a constant, because u is a constant. So because variables are t and x only, so this is t is equal to, this is x is equal to u. So what is the common or bounded area? This triangle. This triangle is the bounded area. So these are two strips parallel to t axis. This is the strip parallel to x axis. Now here change the order. So first we are integrating with respect to x and then with respect to t, because here the order is t and x. So now we will interchange the order x and t. So now what we will do? We will do this. So left hand side as it is, is equal to the right hand side. The right hand side limit is now integral and first integral. So now first we are integrating with respect to x now. So we can take this yt outside. So this is yt. Then integral, second integral. Then with respect to x. So with respect to x we can take this integral inside. So dx upon u minus x raised to the power 1 minus alpha, this part, and then x minus t raised to the power alpha dx, and then dt. So now we are integrating with respect to x first and then with respect to t. Fine. Now as far as the limit is concerned, so first we are writing the limit of x. What is the limit of x? Here x varies from this, that means x is equal to here, here to here. Here on this line x is equal to t, so t is the lower limit. At this point x is equal to u, so this is the upper limit. Now limit of t varies from here to here, that means here t is equal to 0 and here, but this is t is equal to x. So when highest limit is there at this point, you will see that here x is equal to u. So at this point, and since this line is x is equal to t, so when you put x is equal to u here, so t is also u. That's why upper limit is also u. Fine. So here we are taking this to this actually. Here t is 0, here t is u. Fine. So this is the limit. Now let us assume the second integral, this internal integral, as capital I. And first we will try to solve this. Fine. So here is the integral. So I is t to a u dx upon u minus x raised to the power 1 minus alpha x minus t raised to the power. This is the internal integral. Now to solve this integral, we will do, what is our purpose? Our purpose is to change this limit from t to u as 0 to 1. So to do this, we will convert the limit. Basically we need a transformation. So what is the transformation? U minus x divided by u minus t is equal to z. We will use this transformation so that finally we will have the limit 0 to 1. Fine. So you can see, you can check, when x is equal to t here, this will provide you z is equal to 0, and when x is equal to t, then you will see limit will be 1. Fine. So we will convert the limit from t to u as 0 to 1 with the help of this new variable z. So now from here we can rewrite this transformation u minus x upon u minus t is equal to z as x is equal to u minus t into z. Fine. We are writing this x. So this, in terms of x, we can write this as this. Now differentiate this, because here the variable is x, that's why we are writing for x. So now differentiate dx. In the right hand side the variable is now z. So dx is equal to this will be 0, this is a constant. So dx is equal to minus u minus t dz. T is also be considered as constant. We are dealing with only x, and we are writing this in terms of z. So x and z are the variables. However, u and t both are constants at present. Fine. Now here, as far as the limit is concerned, put x is equal to u here, so we get 0, and put x is equal to t here, so we get 1. So z is 1 to 0 minus dx is this divided by u minus x. So from here u minus x is z into u minus t. So that's why u minus t raised to the power 1 minus alpha and z raised to the power 1 minus alpha. Now the second term is this. So in this bracket, first write down x. What is x? From here u minus t into z. So this is written here. Then minus t, so minus t raised to the power alpha. Now from here you can take u minus t common. This is u minus t, and u minus t is here, so you can take u minus t outside. Fine. So in the next line we are having limit. You can interchange these two. So we are having lower limit 0, upper limit 1. So we will have a minus sign here. So minus becomes plus. So then u minus t is dz divided by u minus t raised to the power 1 minus alpha, z raised to the power 1 minus alpha, and now you can take u minus t from here common. सो u माइनस टी रेज टू द पावर अल्फा, और अंदर क्या बचेगा 1 माइनस जेड, 1 माइनस जेड रेज टू द पावर अल्फा. Fine. Then if you multiply this u minus t and u minus t, then their power will be added. So alpha is cancelled out with alpha, so we get only 1, and here is also 1, so that's why this is cancelled out. We have only z raised to the power this quantity. जब ये ऊपर जाएगा तो पावर हो जाएगी alpha minus 1. Similarly here we, when this will go to numerator part, so we get 1 minus z raised to the power minus alpha dz with limit 0 to 1. Now this can be further rewritten as z raised to the power alpha minus this term as it is, but this can be written as 1 minus z raised to the power 1 minus alpha minus 1. 1 is added, 1 is subtracted with limit 0 to 1 dz. If you compare this with beta gamma function, which is defined here, so beta gamma function is basically beta mn is 0 to 1 x raised to the power m minus 1 1 minus x raised to the power n minus 1 dx, and the value is gamma n divided by gamma m plus n. So if you compare, what is m is alpha, n is 1 minus alpha, so the value of this integral is beta alpha 1 minus alpha, and from this formula gamma alpha gamma 1 minus alpha divided by gamma alpha plus 1 minus alpha. So here we have gamma alpha gamma 1 minus alpha, alpha is cancelled out with this alpha, so this is gamma 1 is 1, so ultimately we have only gamma alpha gamma 1 minus alpha, and the value of this gamma alpha gamma 1 minus alpha is basically pi upon sine alpha pi, where gamma alpha gamma 1 minus alpha is pi upon sine alpha pi. Fine, this is the value of this. We are directly using this. Now put this value of I in equation number 3. This is the equation number 3. This is the equation number 3 here. So just substitute it here. So we will get this integral is equal to this t to 0 t to u yt, and in place of this we will use I, pi upon sine alpha pi, this. So what we will get? We will get this 0 to u f of x u minus x raised to the power 1 minus x dx is equal to 0 to u yt, and I is this pi upon sine alpha pi dt. Now you can take this sine alpha and pi in the left hand side, and then first we are writing this part, so we get 0 to u yt dt is equal to, जब मैं इसको राइट हैंड में ले जाऊंगा तो ये हो जाएगा sin alpha pi divided by pi integral 0 to u f of x u minus x 1 minus x dx. What is our interest? Our interest is to find out y, so we have to remove this integral, and to remove this integral the best option is the differentiation. So now differentiating both sides with respect to u, because after solving this we will get a function of u, that's why we are differentiating with respect to u along using Lebanese rule of differentiation under the sign of integration. So now differentiating this equation with respect to u, so d by du 0 to u yt dt is equals to sin alpha pi divided by pi d by du 0 to u f of x divided by u minus x 1 minus alpha dx. Fine. Now apply a Lebanese rule. So first is 0 to u. Now first this total derivative will be inside this integral will be nothing but the partial derivative, del by del u yt dt dt, plus now substitute the upper limit here, so y of u, and then differentiate upper limit with respect to this u, so du by du. This u is basically the from the upper limit, and this u is basically from here, minus now substitute the lower limit, so lower limit is 0, so y at 0. Now differentiate this lower limit, that is 0 with respect to u. This is equals to sin alpha pi upon pi d by du 0 to u f of x upon u minus x raised to the power 1 minus x dx. Now in the left hand side if you will see, this is the function of t, this is with differentiating with respect to u, so this will be 0, so this is 0, plus here we will get 1, so y of u, minus this will be 0 because this 0 is a constant, is equal to this right hand side as it is. So from here f of u is this, So f of u is given by sine alpha pi upon pi d by du 0 to u f of x u minus x 1 minus alpha dx, and now replace u by t, so we get this equation. So this is the solution. This is the solution. Fine. This is the solution. Now take example. Example number 1. Solve the singular integral equation x is equals to 0 to x yt divided by x minus t raised to the power half dt. So if you compare this equation with your Abel integral equation, so f of x is x here and alpha is half. This power is half. So this is the fine. So if you compare, alpha is half. So now you directly substitute these values in this solution. So yt is equals to sine alpha pi upon pi d by dt 0 to t f of x divided by t minus x raised to the power 1 minus alpha d alpha. Now what is alpha? Alpha is half. So sine pi by 2 divided by pi d by dt 0 to t f of x. F of x is x. So x upon t minus x raised to the power 1 minus half dx. Fine. So but sine pi by 2 is 1. So 1 by pi d by dt 0 to t x upon t minus x raised to the power half dx. So now aim is to solve this integral. This is 1. So now let us assume that this integral has capital I. So I is 0 to t x upon t minus x raised to the power half dx. Fine. Now assume this t minus x, this part, as new variable. So t minus x is, since this is half, so that's why we are assuming this as z square. Now here the integral is taken over x. So x is the variable and we are assuming this part with respect to as a z square. So x and z both are the variables, however t is a constant. So from here you can find x. So what is your x? X will be x is equal to t minus z square. Now differentiating, so we get dx is equal to minus 2z from here dz. Now substitute it here. What is x? From here t minus z square. T minus x is assumed as z square. So z square raised to the power half means z. Then dx is minus 2z dz. Now the limit when x is 0 here. When x is 0, you will see x is 0. So t is equal to z square. That means z is root t. When x is t, so t minus t 0. That's why 0. Now you can interchange these two limits, so we get minus sign, but minus sign and this minus sign will be positive. So ultimately 2 limit is 0 to square root of t minus z square dz. Fine, this z is cancelled out with this z. So 2, now integrate this and substitute the limit, we get 4 upon 3 t raised to the power 3 by 2. So this is the value of I. Now substitute this value of I here. So what we get? Yt is equal to 1 by pi d by dt of this integral, but this integral is 4 by 3 t raised to the power 3 by 2. Differentiate this. So 1 by pi 4 by 3 3 by 2 t raised to the power half. So this is 2 by pi root t. So this is the solution of this integral equation. Fine. So here is the Abel integral equation. Similarly, we have another example. This second example, solve the singular integral equation as equation known as Cauchy integral equation. So this is basically the Cauchy integral equation, but we will solve this with the help of Abel integral equation. So what is f? If you compare this with Abel integral equation, what is f of x? Is x square, alpha is 2 by 3. Because what is your Abel integral equation is this. Abel integral equation is this. Alpha is 2 by 3. Fine. Alpha is 2 by 3. Now again, this is the solution of Abel integral equation. Yt is equal to sine alpha pi upon pi d by dt 0 to t f of x t minus x 1 minus alpha dx. Substitute these values. So sine 2 by 3 pi upon pi d by dt 0 to t f of x means x square t minus x raised to the power 1 minus 2 by 3 dx. So this, the value of this is root 3 by 2. So root 3 by 2 pi d by dt 0 to t x square t minus x raised to the power 1 by 3 dx. Fine. Now here we can again use transformation. So t minus x is assumed as z cube because here we have power 1 by 3. So z cube. Again find out x here and then differentiate. So we get dx is equal to minus 3z square dz. Substitute these values here. So root 3 by 2 pi d by dt. Now limit. When x is 0, so z is t raised to the power 1 by 3. And when x is t here, so 0. So t minus z cube, x will be from here, t minus z cube raised to the power 2 divided by this t minus x is z cube. So z cube multiplied by 3 obviously z. Then dx will be minus 3z square dz. Now again interchange these limits. So that will give you a minus sign. Minus and minus becomes plus. So root 3 by 2 pi d by dt 0 to t raised to the power 3. 3z, because here is z square. So one power will be cancel out. So 3z t square. Now open this. So this, and then simplify this integral and then differentiate this. Ultimately yt is equal to 9 root 3 by 10 pi t raised to the power 5 by 3. So this is the solution of this Abel integral equation. Fine. So now in the next video I am going to discuss the solution of this general form of Abel singular integral equation. This is a general form because here we are not taking x. In place of x we are having hx. In place of t we are having ht. So this is the general form of Abel integral equation. Fine. So now we will solve this integral equation in the next video. Thank you.